Hello everyone, welcome to today's session. In my last class I discussed on histogram matching, right? Also I derived the expression for continuous intensity values in histogram matching. So let us consider an example to illustrate that, okay? So assuming continuous intensity values, suppose that an image has the intensity PDF PR of R, which is equal to 2R by L minus 1 whole square for R ranging from 0 to L minus 1 and PR of R is equal to 0 for other values of R. For other values of R. Find the transformation function. Find the transformation function that will produce an image whose intensity PDF is Pz of z, which is equal to 3z square by L minus 1 whole cube for z varying from 0 to L minus 1 and P of z is equal to 0 for other values of z. So this is an example problem on histogram matching. So look at this problem. Assuming continuous intensity values, suppose that an image has the intensity PDF PR of R is equal to 2R by L minus 1 whole square for R varying from 0 to L minus 1 and PR of R is equal to 0 for other values of R. Find the transformation function that will produce an image whose intensity PDF is Pz of z is equal to 3z square by L minus 1 whole cube for z varying from 0 to L minus 1 and Pz of z is equal to 0 for other values of z. So here this means in this problem they have given the probability density function of the input image, okay, and they have given the specified probability density function. So you need to find out the transformation function that will produce this specified probability density function. So this can be done with the help of expressions which I derived in my previous class, right? So first thing, in order to find out the transformation function, so we have a formula. So that is equal to the transformation function S is equal to T of R. We know this. And the transformation function what we have considered for this continuous intensity values from the given PDF we can identify that this is the continuous intensity valued image. So we have to use the formula of continuous intensity values. Okay, so TR of R is equal to L minus 1 summation 0 to R PR of W dW. Okay, so I call this as equation number 1. Now what is this? W is just a dummy variable of integration. Here we are referring to input probability density function PR of R. So substituting this given value in this particular equation, so S is equal to L minus 1 integral of 0 to R. So here this expression is replaced by W as we have used a dummy variable W, L minus 1 whole square dW. Now simplifying this expression, taking the constant terms outside. Here the constant terms are 2 and the denominator term. So S is equal to 2 into L minus 1. I am taking 2 by L minus 1 whole square. The constant terms outside the integration. So 0 to R W dW. So this term cancels. Okay. So now further simplifying this results with 2 by L minus 1 integral of W with respect to dW. So this is equal to, I'll write directly. So this is equal to R square by 2. So here this term cancels. So S is equal to R square by L minus 1. So I got the transformation function. Yes, right. So what is the next step here? So here since we are concentrated towards the specified probability density function, so the transformation function for specified probability density function is represented by G of Z, right, and it is given by L minus 1 integral of 0 to Z P Z of, instead of Z, here I will use one more dummy variable, that is T. This is equal to dt, where T is a dummy variable of integration, and here we are referring to the specified probability density function, that is Pz of Z. So this is equal to, so G of Z is equal to L minus 1, substituting the specified probability density function inside the integration. So this is equal to 3t square divided by L minus 1 whole cube dt. Now further simplifying this expression, you have to take the constant terms outside the integration, which results with 3 into L minus 1 whole divided by L minus 1 whole cube integral of 0 to Z t square dt. Now this term cancels with this term, okay, and you will be left with square here. So this is equal to 3 by L minus 1 whole square, and simplifying this results with Z cube by 3. This term cancels, therefore G of Z is equal to Z cube by L minus 1 whole square. Okay, this I call as equation number 3. Now what is the next step here? So we know that G of Z is equal to S. So substituting for G of Z here, so this results with Z cube divided by L minus 1 whole square is equal to S. So retaining Z on LHS and taking all the terms towards RHS, so this is equal to, Z is equal to L minus 1 square into S whole power 1 by 3. Right, now what is this S value? We know that from equation number 2, S is given by r square by L minus 1. So from equation 2, I am substituting the value of S here. So this is equal to Z is equal to L minus 1 whole square, and here r square by L minus 1. Right. So again this square and this term cancels. So we will result with, I'll continue here. Okay. So the Z is equal to L minus 1 into r square. This I call as equation number 4. So this is how you need to find out the intensity levels of the processed image for the specified probability density function. So if at all you observe this expression Z is equal to L minus 1 into r square, here you can see that there are two steps of mapping. Okay, so here R is first mapped to S and S is next mapped to Z. Therefore R is mapped to Z. Okay, so we can find out the intensity levels of the processed image by using the input image intensity level directly. Okay, so this is how you can solve a problem on histogram matching for continuous intensity values. Okay, so now let us see the case of discrete intensity values. Okay. So now let us consider the histogram matching for discrete intensity values. We already know that for discrete intensity values, the transformation function formulation is given by. So directly I'll write the transformation function for discrete intensity values is formulated as Sk is equal to T of Rk. We know this, right? And we also know what is this T of Rk here. So this T of Rk is equal to, since it is discrete intensity values, here here intensity is replaced by summation. Therefore this is equal to L minus 1 summation j equals 0 to k PR of Rj. So what is this PR of Rj? So this is normalized histogram, and this normalized histogram is represented by PR of Rj is equal to Nk by Mn, where M and N represents the total number of pixels in the image or the size of the image. Okay, and we know the Nk is the number of pixels having that kth intensity value for k varying from 0, 1, 2 up to L minus 1. Okay, so now substituting this in the above equation, Sk is equal to L minus 1 summation j equals 0 to k. So this becomes Nj divided by Mn. So taking the constant term outside this summation, it results with Sk is equal to L minus 1 by Mn summation j equals 0 to k Nj. This I call as equation number 3. Okay, so here this is the transformation function for the input probability density function, but here we are concentrated with the specified probability density. So the transformation function for specified probability is formulated as G of ZQ. So here this is equal to L minus 1 summation I equals 0 to Q. So here instead of input probability density function, here we define Pz of Zi. Okay, so now this I call as equation number 4. Okay, but we know that this G of ZQ is equal to the transformation function. Since these two transformation functions are same except for the variables, we call this as T of Rk, which is nothing but G of ZQ is equal to S, where ZQ is equal to G inverse of S. This I call as equation number 5. So now here for discrete intensity values, again the intensity values of the processed image can be easily calculated using the inverse transform of the transformation function of the input signal. Okay, so here S is mapped with Z with inverse transformation. So these are all the expressions which are used for which are used in histogram matching for discrete intensity values. Okay. So next is, let us solve a problem on this histogram matching for discrete intensity values. Okay. So now look at this problem. This is a problem on histogram matching, okay, for discrete intensity values. So perform histogram matching for a 3-bit image of size 64 cross 64 using the following data. So we have performed histogram equalization for this same image in my previous class, right? So the histogram matching is just the continuation of that. That means we are using the same values of histogram equalization for finding the actual values in histogram matching. Okay, so this is the given image. So the image is having Rk, number of intensity levels, and Nk is the number of pixels having these kth intensity value is given in this column number 2. So using this Nk, we also can find out the total number of pixels, which is equal to the sum of this is the size of the image. Next we need to find out the normalized histogram. So already in my previous class I have told you how to find out this normalized histogram PR of Rk, which is equal to Nk by Mn. That means NK for this or not, NK is 790 divided by the total number of pixels in this particular image. So this gives 0.19. So similarly for each NK value and it is divided by the total number of pixel results with this normalized histogram value as written in column number 3. So we can plot a graph of this. So this is equal to RK versus PR of RK 0, 1, 2, 3, 4, 5, 6, 7. So the maximum amplitude is 0.25. Point 5, 0.15, 0.20. So at RK is equal to 0, it is equal to 0.19, approximately it is here 0.19, and for R naught or 1 it is equal to 0.25. So this is equal to 0.25, and at 2 it is 0.21. Approximately this is equal to 0.21, and at 3 this is equal to 0.16. So approximately this is equal to 0.16, and at 4 this is equal to 0.08. So it is somewhere here 0.08. For 5 it is 0.06. For 6 it is 0.03. And for 7 it is 0.02. So this is the normalized histogram for the given input image, that is PR of RK. Next we need to find out the transformation function SK using the formula, and I have done all these in my previous class, so refer that. So SK is obtained by using the formula, transformation function formula. So this SK values are rounded off to its nearest integers. So this becomes 1, 3, 5, 6, 6, 7, 7, 7. Okay. So next, and the probability density function of this histogram equalization is given by 0.19, 0.25, 0.21, which is corresponding to these values. For 1 it is 0.19. and for 3 it is 0.25, and for 5 it is 0.21, and you have 2 6 here. So for 6 it is the sum of 0.16 and 0.8, it is equal to 0.24. You have 3 7 values here, so the sum of 0.06, 0.03, 0.02 results with 0.109. Okay, so now this is the histogram equalization. Today, now in this problem, we need to find out histogram matching for the specified probability density function. So this is this second table contains the specified probability density function Pz of Zq. This is given in the problem. This is given in the question. So this is the specified probability density function for a particular application. Okay, and Zq represents the intensity level. Okay, and now let us plot a graph of the specified probability density function Pz of Zq for Zq values 0, 1, 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, and maximum amplitude is 0.30. So 0.10, 0.20. For Z0 it is equal to 0, for Z1 it is equal to 0, for Z2 its amplitude is 0, and for Z3 it is 0.15, so approximately it is here, so 0.15. For Z4 it is 0.20, so approximately it is here, 0.20. For Z5 it is 0.30, 0.30, and Z6 is 0.20, Z7 is 0.15. So this is the specified probability density function given in the problem. So what we need to find out is that, so using the transformation function, we need to find out the actual intensities. Okay, so for that we know the formula of the transformation function for the discrete values. G of ZQ is equal to L minus 1 summation I equals 0 to Q P Z of Z, or I can call this as Zi. Okay, so this is the formula to find out the transformation function. So using this formula, first I'll find out for Z is Z naught, that is Z is equal to 0. For Z is equal to 0, G of Z naught is equal to, what is L minus 1? The maximum intensity levels here is 8. So 8 minus 1 is 7. So 7 summation I equals 0 to 0. Here Q is equal to 0. Sorry, for Q is equal to 0, Z naught is equal to Pz of Z naught. So this becomes 7 into Pz of Z naught, which is equal to, what is Pz of Z naught? It is equal to 0. Okay, so for Q is equal to 1, G of Z1, again using the same formula, I equals 0 to 1 Pz of Z1, which is equal to this value, that is 7 into Pz of Z0 plus 7 into Pz of Z1. Even this is 0, this is 0, therefore the result is 0. Next, for Q is equal to 2, G of Z2 is equal to 7 into summation I equals 0 to 2 Pz of Z2. So this whole value 0 plus 0 plus 7 into Pz of Z2. Pz of Z2 is also 0. So this is 0. Similarly, next let us find out for Q equals 3. So now here I will just create a table of ZQ versus G of ZQ. 0, 1, 2, 3, 4, 5, 6, 7. For 0, 1, 2, G of ZQ is equal to 0. Now for Q is equal to 3. G of Z3 is equal to 7 into summation I equals 0 to 3 Pz of Zi. So this is equal to 0 plus 0 plus 0 plus 7 into Pz of Z3 is 0.15. So this results with 1. Okay. So next is for Q is equal to 4. G of Z4 is equal to 7 into summation I equals 0 to 4 Pz of Zi. So all these values, 1 plus 7 into Pz of Z4 is 0.20. So this into 0.20, this results with 2. Okay. So similarly, for 3 it is 1, for 4 it is 2. Similarly, using the same formula, we need to find out the other values of Q. Then it results with, okay, so this is G of ZQ value. Okay. So now once I got the transformation function G of ZQ, now plot this graph. ZQ versus G of ZQ, 0, 1, 2, 3, 4, 5, 6, 7. So this is equal to 1, 2, 3, 4, 5, 6, 7. Okay. So here this is 0, this is 0. For 3 it is 1. For 4 it is, and just remember the transformation functions are monotonically increasing function. So it is 1 here. So and it is 2. For 4 it is 2, and for 5 it is 5, and for 6 it is 6, for 7 it is 7. Okay. So this is the transformation function. Okay. So here the g of zq value which I have got, I have rounded up to nearest integer values. Okay. I have considered the round off values for nearest integers, and this is the transformation graph for this. So how to find out the actual values from this? Now look at this zq and sk versus zq. So here I have the zq values for 3, 4, 5, 6 and 7, and the sk values are 1, 3, 5, 6, 7. So I am mapping sk to zq. Okay. So here from the formula we know that we should perform inverse mapping to get the zq value. So if at all I go with the inverse mapping for zq3, this is equal to 1. So 1 is 0.15. For z3, this is equal to 0.19. Okay. And for z4, it is 2. For z4, here from this it is 0.25. Just I am performing inverse mapping from zq to sk. Okay. So here for this is z3, this is z4, z5, z6, z7. So for z5 now, for z5, so sk is 5, so the 5 value corresponding probability density function is 0.21. And for z6, sk is 6, so for 6 the corresponding probability density function is 0.24. And for z7, the corresponding sk is 7, and the probability density function is 0.109. So the remaining probability density functions are 0. So this is how you can find out the actual pz of zk. Okay. So first you need to find out the transformation function using the formula, and the values of that is rounded off as I have written in this table. And now I am considering zq values. I am performing inverse mapping with sk, so that the corresponding sk mapped values probability density function becomes the actual values of this specified probability density function. The last thing is that you also have to plot a graph of this p of zk versus zq. This is the last step in this. So let me finish this part. So here you need to plot the graph of zq versus pz of zk. So 0, 1, 2, 3, 4, 5, 6, 7. So this is equal to 0.25, 0.5, 0.10, 0.15, 0.20. So this is equal to, for 3 it is 0.19. For 4 it is 0.25. For 5 it is 0.21. For 6 it is 0.24. For 7 it is 0.101, that is nothing but 0.11. Okay, this is how you can plot the actual values, actual probability density function, that is the histogram matching values with the ZQ values. Okay, this is all about histogram matching for discrete intensity values. Thank you.